The first problem's topic was flow through porous media, and the goal was to find how long it would take to fill up the dog's bowl using this nice homemade filter. So the related equations are the Bernoulli equation, the extended one, Darcy's law, the volumetric flow rate, the height, volume of the cylinder, and the Reynolds number. The assumptions made here were laminar flow because the word trickles was included in the description, so that would cue into it moving slowly. And that allowed us to assume that Darcy's law applied, so you can use that, and that the velocities at point 1 and 2 are negligible, and delta P equals 0, so it's assuming that this water flows purely due to the difference in height and gravity. The cited properties used are the density and the viscosity, which are both found at table A-9 at 20 degrees Celsius. To find the solution here, the Bernoulli equation was simplified, so you get the friction is equal to the gravity times the differential height, and then from there you can find the superficial velocity and use that to find the volumetric flow rate. The time is then equal to the volume of the dog bowl, as seen in the equation above, pi r squared height, and then you got that to be 10.03 minutes, so a little bit of a wait, but not too bad. And then the Reynolds number was verified, and it was found to indeed be laminar. The next problem discussed internal fluid flow with friction loss and pump analysis, and you're trying to find the required pumping head to maintain flow rate and drawing the typical centrifugal pump curve. The equations used were the head form of Bernoulli, the velocity equation, the Reynolds number, and head loss in a pipe, and then the friction factor for both laminar and turbulent flow. The assumptions made were that alpha equals 1, and then the velocity at point 1 is much less than velocity at point 2, so it's negligible, and starting out at a height of Z2 equals 0, and P1 and P2 are both at atmospheric pressure. The cited properties are density, viscosity, and then both of these were from table A9 at 15 degrees Celsius, and then the KL, the loss coefficient, is 0.5 found in table 8.4. So the solution of this one, first you would simplify the energy equation to get the pump head, and then you found the velocity of the liquid, the Reynolds number, so then you know that the first part at least is turbulent, and then you calculate F prime. With that, you can find the head of pipe 1, and then you need to do the same thing for pipe 2, so find the velocity, then the Reynolds number. Found that the second part of the pipe is actually laminar. We did sigma over D, roughness, and then F prime again, but this time for laminar. So you can find the head of pipe 2 and then the total loss. You just sum those together, and then you find the total required pumping head. And then for B, this is just a typical pump curve. You see the pump performance curve, the systems curve, and operating point, and then SI units are feet in grams per minute. So this next problem covers external fluid flow. The related equations used here were the drag equation, and to find the weight force and the buoyancy force, the area, the volume, and the Reynolds number. The assumptions made was that the water flow over the sphere is laminar, and then the cited problems were from table A9 at 20 degrees Celsius for water. So the solution for this one is you find the forces on the ball, do a force balance, force drag equals weight minus the buoyancy force. Then you evaluate that, so then you're able to solve for V and substitute that into that equation, and then last but not least, verify that it is indeed laminar flow, so these equations apply. Question 1 addresses compressible flow and more specifically choked flow. The equations used were for the speed of sound, the Mach number, the stagnation temperature and pressure, and the critical pressure. The assumptions were one-dimensional isentropic compressible flow for an ideal gas, assuming this ideal gas is air, which leads us into the properties K equals 1.4, found from table A13, and the CP value found in table A1. The solution then is first solving for the C constant, and then using this number to find the velocity, because we're given the Mach number. And then from here you can find the stagnation temperature and pressure, and then you finally solve for the critical pressure. The physical meaning of this is if you were to lower the pressure anymore, the mass flow will not further increase. The last problem is on microscopic mass momentum balances, boundary conditions, and analytical and numerical solutions to Navier-Stokes. It's a slide at the playground that has unfortunately been filled with water, but Polly is going to analyze it for its analytical and numerical velocity in the z direction. The equations used for the continuity equation in spherical coordinates, the z component of the compressible flow for Navier-Stokes, because that's in what direction the velocity is going in, the finite differencing equation, and the assumptions made were steady state, which makes the time derivative go to 0, irrotational, which makes the theta derivative go to 0, Newtonian, laminar, incompressible, so the rho can be pulled out and then divided over to the other side, making it 0, fully developed. So there's only velocity in the z direction, not the r direction or the theta direction, no slip at the walls and symmetry, which are for the boundary conditions. And delta p equals to 0, so that means it only flows due to gravity. The cited properties here are the viscosity, which was found in table A9, and also rho, the density, also found in table A9, and these are used in the numerical solution in the Excel spreadsheet. So the solution was first to simplify the continuity equation. You can see here with the assumptions made, steady state, incompressible, fully developed, things cancel out, and then you're left with that dz equals 0. And then you use that to simplify the Navier-Stokes equation. So again, with the assumptions, you are left with negative rho gz sine theta equals that term on the right side. So next you need to define your boundary conditions. You've got symmetry because it is a symmetrical pipe, no flex in the middle, and no slip because the walls of the pipe are not moving. So next you can use that information to integrate twice for Vz, and then you can apply these boundary conditions, and then you get your analytical solution. Next you solve numerically, so you need your node equation. So you take your result from the continuity equation, and then you can separate that out so you get that second derivative and duz dr, that first derivative, which you have the equations for. So you substitute the equations listed previously in and then solve for uz and n, and then with all these things in Excel, you turn the iterations on, and then you're able to solve for the numerical solution, and then you can compare it to the analytical solution. Also, it should be noted that this is turbulent, proven by the Reynolds number, but we don't know how to solve those, so we're just going to go with laminar, but it's not right for the real world.